Welcome back to ECE 501B. A few announcements, and they are all concerning today. Homework number 8 is due today. Project deliverable 2 and 3 is due today. And teacher course evaluations are due today. Those evaluations are anonymous. I have no idea who's sending what, but they are helpful to me to understand how I can improve upon the course, make it better for the next time, and what I can do differently to enhance what the students see in 501B in the future. If something worked well this semester, hopefully I will see that in the teacher course evaluations. I do have one more announcement that I should include here. Not only, I guess I do have it in the office hours below. Before I get into office hours, let me just remind you that the final exam is on Tuesday, and it's in the evening. It's a couple of hours later than our normal class time. It's at 6 o'clock to 8 o'clock, and it's in this classroom, and it will be a 2-hour final exam. There is practice or final exam material or information on D2L in a final exam unit, and I think there's even a review lecture that I've made from earlier semesters that will be appropriate to this semester. Office hours are the same this week. Thursday and Friday's office hours are still 9 to 10 and 10 to 11, but Monday, since we don't normally have a final on Tuesday or a class on Tuesday, and we haven't had office hours on Monday, there's an additional office hour on Monday leading up to the final exam, which is Tuesday at 6 to 8. Relative to the final exam, the process really hasn't changed too much relative to previous midterm exams, except maybe now you have one more sheet of notes. I think before you had 3 sheets of notes. Now you get an additional sheet, and that can be front and back. And the final exam will be comprehensive. In the way that the material is structured during the semester or this class, really sort of one question at the end could be considered comprehensive because you're learning or you're using previously learned material to answer that last question in the class. But you may want to bring a calculator. I'm not sure how much you will be needing that, but you won't be allowed a cell phone or a computer or a textbook or the course notes. Questions on the exam process? Yes? There won't be a sample exam for this class posted under or on the course website. But there is a review lecture, and that sort of, again, recaps what you've seen this semester, and it shows it to you now as a whole in terms of, okay, now you can sort of say, if this is linear algebra done right, let me see what that really means. And now you've seen the full picture. Now you can start to understand maybe how the beginning foundational material builds up to this last piece of information, which deals with trace and determinant of an operator. So if I was to practice for this exam, I would practice by looking at the old exams, probably first, and not forget or not discount the information or the material since the last midterm, because it's going to be comprehensive. With that said, the material on infinite dimensional vector spaces won't be presented unless we have to do something like an earlier exam where you were dealing with the Gram-Schmidt process for these polynomials, if you view those like functions. But the second textbook material won't be on the exam, but then I would say look at the old exams, practice those, and concentrate on the homeworks that discuss or deal with material since the last exam. Then I would start going back. So this is sort of a hierarchical approach if you're limited in time. Then I would look at the previous homeworks, and then I would start looking at the notes, and then I'm not sure what I would do beyond that unless you want to try to find new material from different sources, new sources, but that's now assuming that you have an unlimited amount of time to prepare for the final. So I would look at focusing on the old exams, homework since the second exam, previous homeworks, notes. I guess you could watch all the videos again if you need to take some naps occasionally. You can start those up, and you'll then be put to sleep trying to study for the final. But sleep is very important, as is exercise and nutrition, in successfully completing this class. So don't spend the next however many hours it is between now and Tuesday, almost a full week, studying exclusively and neglecting your health in trying to successfully succeed on this exam. But that's what I would do in terms of suggestions for how to approach preparing for the final exam in this class. Yes, so exam 1 and exam 2, and then you can look at previous semesters exam 1s and exam 2s. That's what I'm meaning by old exams. So you not only have your exams with the solutions now, but you also have previous semesters exams on the D2L website that you can refer to. Today we are going to continue with our infinite dimensional space discussion, the second book, and actually what I want to do is sort of step through maybe the first 5 chapters in a very outliney way so that you can sort of see the big picture, and then we'll jump back into the first part and start talking about signal sets, set partitions, and when you see signal sets, now connect that. What you're wanting to do now is rely on this foundation that you've built up all during the semester. Meaning we started out with trying to create vectors in finite dimensions, and we had sets of vectors. Now we have signals, functions, and we'll have sets of signals or sets of functions. How do we now put these into similar behaviors or similar sets? Now can we partition these sets so that we now have sets of signals? And in that way, can we define equivalence sets or equivalence classes? Once we have that, can we start turning these into signal spaces like we had with vector spaces? Can we establish a distance? Can we have some kind of metric? What does it mean with this metric for that vector or signal to have a non-negative distance or a positive distance? What do we mean when we want to talk about distance? Now that we have signals and this metric, we now have a metric space that's now applied to not just these tall, thin columns, which were vectors, but now we're applying those to our sets that are containing functions or signals. And we want to now talk about or deal with signals that we can represent or describe or measure with these metrics. We also then will be thinking about convergence. Do we have a way, now that we have a distance measure, can we establish that we have this collection of functions that might be approaching a particular function that might belong or may not belong to our underlying space or our underlying set? Do we have convergence? If we have convergence, that means that where we are approaching in terms of this function, that function is, in fact, a part of the underlying set. If the sequence of functions is converging to something outside the original set, then it's not going to be convergent. in terms of it's not approaching something in our original set. Convergence, as you will learn in this context, now means that if you have a convergence sequence, you also have a Cauchy sequence. And a Cauchy really will define that, but a Cauchy sequence means that you could now look at, for a large enough maybe index on these functions, if you have two functions with a high enough index, the distance between those two functions will be vanishing. And that's now a Cauchy sequence. And if that sequence now, or Cauchy sequence, converges to a signal in the signal space, then we say that you have a complete metric space. If it didn't approach that particular function, then you would have it wouldn't be a complete metric space. And one way to look at that, they talk, and we may get to that in this lecture, we may not, but suppose that you now had some waveform that looked in one of its indexed functional forms might look like that red curve. And now as you increase the index on that waveform, now maybe it gets steeper in terms of a continuous wave through the origin. But now the limit of that, now that you have this discontinuity right at the origin, or right at zero. So that the convergence, or this particular sequence, is not complete. Depending on how we've defined our metric, we may be the signals may be getting closer and closer to each other, the blue and the red, or if we continued on in the direction of the blue, it might continue to get closer and closer, but in the limit, you now have something that's -1, +1, and there's no continuous connection between -1 and +1, so that particular end function is not continuous. So if we were talking about a continuous set with a particular metric, now the signal that we converge to is not continuous, and so that would not be a complete set in terms of that continuous set of functions would not be a complete set, or it would not form a complete metric space. The sequence limit would not have belonged to the set. If the sequence limit belongs to the set, then you can say that you have a convergent sequence of functions, or that you have convergence. And in general, now you can think of, if you have a convergent sequence, that implies that you have a Cauchy sequence, but that previous example that I just illustrated, the red and the blue, and you're now continuing to get steeper and steeper, that could be a Cauchy sequence, but it's not convergent, because where you're approaching doesn't belong to this set of continuous waveforms. Now you have a discontinuity at zero. And so you're not always necessarily going to have a Cauchy sequence implying that you have a convergent sequence. The limit of that sequence may not belong to the underlying set, which in that case was this set of continuous waveforms or continuous functions. Again, I'm trying to give you sort of this big picture description of how all of this sort of steps through, just like we did with the finite dimensional case, where we started with vectors, then we started talking about linearly dependent, linearly independent. We may now want to talk about, can we have a separable metric space? And that now really just means that we have a countable covering that we can impose on that particular space, contrasting that with a compact metric space, which really now sort of says that you have bounded or a set of functions over a bounded interval, then you have a compact metric space. You could cover that with finite covering. We now have these functions. We can talk about introducing these properties of addition and scalar multiplication on those functions. Now we have a linear space. We have linear combinations of these elements or vectors, and we can now talk about linearly independent. What did we say when we had a linearly independent set of vectors? What was one way of describing a linearly independent set of vectors? Do you remember? So now if we were linearly combining these vectors to form the zero vector, the only way that that would happen if those vectors were linearly independent would be if those scalars were all equal to 0. And you can do the same kind of description for functions. Now the only way to have a zero function, a function that's 0 for all independent variables, now you would have to have the scaling of each of those functions equal to 0 if those functions are linearly independent. And you can now start talking about linear subspaces, meaning maybe you have a function that can be described by a linear combination of an underlying set of linearly independent functions in that set. We can also now introduce a norm, and we now have this concept of length. In terms of a vector, the norm of a vector sort of measured its size. Here, can we measure the size of a function? Can we do that with a norm? Can we introduce this normed behavior? And if you do that, and all of these Cauchy sequences actually converge to a function in the set, then you will have a normed linear space that is complete. That's now a Banach space. So that when you now start getting beyond this class and somebody might start talking about Banach spaces, now you can start to maybe connect that with what you've already done in finite dimensional spaces. You now have a normed linear space that's complete. And that's now a Banach space. And you can then contrast that with the next space, but the next space now goes beyond a normed space and it goes into an inner product space. So you can start thinking of these different norms that you could introduce, the L1 norm, the L2 norm, the L3 norm. Which of those norms actually generates an inner product? Well, maybe it's the L2 norm. And if it's the L2 norm, then that, if we have a space that contains or possesses an inner product, where the inner product gives us the concept of angle, now we say these functions, if we look at the inner product of two functions, we can talk about the angle between those. And if we wanted those functions to be orthogonal, what would we want to know, or what would we be looking for in terms of their inner product? Now we want those functions to no longer line up, do we? We want those to be orthogonal. So we want the inner product to be 0. If we have an inner product on this set, then we can start talking about orthogonality of these functions, just like we did with vectors. So we have this concept of angle. Now we can talk about projections. Can you project this function x onto this sinusoid like we did last time? We were dealing with inner products and we were doing the Fourier expansion. Can you now, if you have this inner product, attach that to a space that's complete and it's linear? Now you have this Hilbert space. A Hilbert space is an inner product space that is complete. Complete meaning, if you have this sequence of functions that are converging, the limit of that sequence that's converging belongs to the set. So that now you have a different space, a Hilbert space. Now you can talk about orthogonality, and maybe you couldn't or didn't in a Banach space. So we're progressing to more and more sort of fine-tuning of the space and potentially stronger results can be achieved with these different spaces. We might get into, I don't think we'll get that far, but time ambiguity function. Now can you connect or talk about the distance between a function or its waveform and a translated version of that? If a function was highly sort of unique in one particular time in its independent or against its independent variable, then as you shift it with time, it's not going to overlap or be correlated with a unshifted version of that waveform. Meaning if you now had a waveform that might look like that, it's going to not line up, or maybe that one would line up more strongly versus one that if you shifted those two in time, let's say you shift the top one, its correlation will be stronger than the bottom one if you shift them the same amount in time. And how do you sort of judge that? Well, if we have a measure of distance, we might like to know how do these functions now align with themselves. And you've probably heard of correlation or autocorrelation, and you can now start to measure that or account for that if we have the appropriate mechanics or machinery in our mathematics. And if we now have these functions that we can decide or that we can determine are linearly independent, and if we can figure out if they are orthogonal, if we have an inner product, now we can start doing bases. We can do orthogonal basis, and we can even do orthonormal basis, and we've done that with a few examples. And you can do it either with the finite dimensional setting or the infinite dimensional setting, which now is this Gram-Schmidt that allows us to just continually remove more and more pieces that are in orthogonal directions to the signal space that you're dealing with. And we can now think about what happens when you start describing functions in terms of these orthonormal basis sets. And remember, or recall maybe the usefulness of being able to do that. Now we can start to describe that by scalar combination of these orthonormal basis of functions. And that really is what you will see in a broad setting with the first 5 chapters in the second book, is this progress or progression of ideas and concepts that now takes us to being able to decompose these vectors, the vectors now being functions, into an orthonormal basis set. And now what can we do once we have that machinery? So to get up to that, now what we want to do is go back to the first part of this first 5 chapters of the book and start talking about signal sets, set partitions, etc. Now that we've already covered the first 5 chapters. That's what I'm suggesting. But that maybe will allow you to more quickly get up to speed if you need to get in and start diving in. If somebody starts talking about Banach spaces, Hilbert spaces, autocorrelation, correlation of functions, now you can start to relate that to what you already know in the finite dimensional setting. So let's talk now about the first parts of this, which deal with signal spaces or sets of signals. And again, we want to continually remind ourselves what we've already looked at or what we already know. And for that, let's now recall that in the finite dimensional case, we in fact started with a set of vectors. And in a sense, then you can start to play this lecture in your mind and say, oh, let me just follow along starting with chapter 1 in Axler. And that's going to be a review for the final, essentially. So that now you can recall we started with sets of vectors. Here, in the infinite dimensional case, we're going to start with a set of signals. So here we will start with a set of signals. Let's just give some examples so that we can start thinking or getting our mind around what it is that we're maybe referring to. Suppose somebody says, let's talk about the set of sinusoids, where now we could define sinusoids many different ways. Let's now just say it's the set, sub s, where the sub s stands for sinusoids, and we could say that that consists of the vectors x, the functions x of t equal to the real part of, let me not use a curly brace again, the square brace, the real part of e to the alpha plus j 2 pi ft plus theta. And let's now say that t is a parameter between minus infinity and infinity. Alpha, f, and theta are all real constants. And you could look at this as just using your knowledge of exponentials. You could say, well, that's now e to the alpha, e to the j, 2 pi ft plus theta. And what's the e to the alpha? Well, now alpha doesn't possess a time constant, or a time, does it? It's not a function of the independent variable. E to the alpha is just some scaling. And these are sinusoids. These are, for all time, some sinusoid of a given frequency f. We're just taking the real part of this exponential, that the one piece is a complex exponential, so now we have e to the alpha cosine of 2 pi ft plus theta for all time t and a given f. So we could just say, let's start with a set of sinusoids. Or alternatively, we could say it's the same set or a similar set, except now this set of vectors x, let's just have those functions satisfy the following partial differential equation. Suppose we now have the set of x such that the second partial of x with respect to time plus lambda squared x of t equals 0. And now that's another way for a given lambda value and for time, which again we are allowing to vary between minus infinity and infinity, lambda to be real. That's another way, or an alternative way, of defining a set of sinusoids. They now have to satisfy this partial differential equation as a function of time. Another set of signals that we could create or work with, we could view as energy limited signals. Here, let's say that we subscript it with an E. We now have this set of signals sub E, energy signals, and the argument maybe here is K, where K is the bound on the energy in that waveform. Where now we might say that our set of vectors x, or the functions x, are such that the integral from minus infinity to infinity of x squared of t dt is less than or equal to k, which is bounded. And now we could say, let's just work with the set of signals that are energy limited. And that's now where we start. Or we might say, what about signals that are limited in their time support, or the interval of time where they are non-zero, or duration limited signals? S sub d, and now let's give it an argument of t, capital T, and we could say that this now is the set of functions x, such that x of t is equal to 0 for all values of the time, absolute values of the time, bigger than capital T. Or what that's really saying is this is a set of functions that are 0 outside of these limits on capital T. Where you can actually start saying things like, oh, if I have a function x that belongs to s sub d of t sub 1, what does that do if x is x? Does it belong to the set of duration limited signals on t sub 2 if t sub 2 is bigger than or equal to t sub 1? Which way does the implication go in this way, or in this particular? Does it go both ways? Does it go towards the right? Does it go towards the left? If you now have a signal, let me draw the signal first so that I can, what are we saying? We're now saying that we can identify a t sub 1, and we're saying that t sub 2 is bigger in absolute value than t sub 1, where this is our signal x of t. What can we say about the arrows or the implication if x belongs to the duration limited signals associated with capital T sub 1, which is what I've drawn? Does that also belong to the set of signals consisting of capital S sub d of t sub 2? So the implication is towards the right and not towards the left, is it? The left implication arrow doesn't exist in that particular example. Those are then time duration limited signals. That's another set. Another set that we could talk about, we might now be interested in their frequency content, and maybe they contain frequencies only up to a certain limit on the frequency, or band limited signals. In this case, we have S sub b, let's say of omega, is the set of signals x such that capital X of f is equal to the integral from minus infinity to infinity of x of t e to the minus j 2 pi f t dt. Let's say that's 0 for all f bigger than some frequency omega. Meaning, this signal x of t has no content, no energy, if we get a frequency higher than omega. That's what I'm trying to say by this sort of Fourier transform argument. We're saying that the capital X of f, the frequency content, is 0 beyond a given frequency omega. And that would then be a band-limited set of signals, or pictorially, now I get into trouble because it needs to be symmetric if I'm now talking in terms of frequency f. If I get in trouble, what I mean is sketching this. That's supposed to be a mirror image from right to left. If it's not, just humor me and assume that it is. But now this is suggesting that capital X of f, or the frequency response of that, if you have a signal x that belongs to this band-limited set, then it has no content or energy beyond omega. And obviously then we've given that omega as an argument in this band-limited description. Once that we now have a signal set or sets of signals, we can now start to apply types of operations that we always have applied to sets, unions and intersections. So we can now apply set operations like union and intersection to signal sets. As an example, suppose that we take now a duration limited signal and we intersect that with a band limited signal. What do we get out there? We now have a time duration limited signal and an energy limited duration signal. What's the result of that intersection? Is there any overlap? Can we have a duration limited, time duration limited signal that has a limit on its bandwidth or a limit on its frequencies? Or can you have a band limited signal that is finite in time duration? Can you create a pulse waveform out of a finite bandwidth spectrum? The answer is no. The only signal that satisfies this is the zero signal, the signal that's zero for all frequencies. This is now the set of x such that x of t is equal to 0 for all of the arguments time. Or what we're saying here is the only signal that is both band limited, meaning we have a finite frequency interval over which it has support, band limited and time duration limited or duration limited is the zero signal. And there, to sort of kick you back into that thought process, recall the Fourier transform. Of a finite duration pulse waveform. Meaning, what does the Fourier transform of this x of t what does that look like? If you found the Fourier transform of that pulse, do you remember what you would have obtained? That's this sink, isn't it? The kitchen, I mean, not the kitchen sink, but it's the sink function. It's sine of t over t, that shape, which does what? That goes on forever, doesn't it, in terms of frequency content. So this particular waveform is duration limited, but it's not band limited. Now your Fourier transform has infinite frequencies in order to be able to create this time duration limited, and you have just the dual of that also. If you now have a band limited waveform, meaning think of the Fourier series. Let's say you have now one sinusoid. What does its spectrum look like? Well, it's band limited, isn't it? It now has one spectral line, let's say at a given frequency. But what is its time domain waveform? It's infinite in extent. So those are the two sides of that discussion that hopefully help you understand that the intersection of a band limited and a time duration limited waveform is the zero signal, or the signal that's zero for all t, or a non-trivial signal. And non-trivial now means something other than the zero waveform. A non-trivial signal cannot be both time duration limited and bandwidth limited. Now we have signals, or a set of signals. Maybe we have this set of sinusoids. Maybe we have a set of band limited. Maybe we have a set of energy limited. Can we start to partition those, or separating those, or making some look like each other? Or what's this notion of partitioning this underlying set, where now we can be thinking of the set of sets, where now we might have partitioned our underlying set into n different sets. So the set of sets form a partition of the underlying set that we might have been working with, or that we are working with. And we then might define that by S. The overall set is now a union of S1 union S2, etc., union S sub n. And what we want is we want these inner sets, or the S sub 1s, the indexed sets, to not have any overlap, so that we can partition things in the overall set, where we want if S sub I intersect F sub j doesn't contain anything, it's the empty set, for all non-equal values of I and j. Or now if we have the cloud, we like to talk about clouds. Now maybe we have a partition S1, S sub 2, S sub 3, S sub 4, S sub 5. And maybe we now have this energy limited set of signals, and maybe S1 corresponds to a certain energy bound. S2 might be some other bound on energy or in some range. So a partition neatly divides a set. And sometimes to create that sets of sets, or a set of sets, it's sometimes easier to think of equivalence relationships or equivalence sets. So often, easiest way to get a partition is via an equivalence relation. Where now two elements, and what are our elements? Those are functions or vectors, whatever, however we want to call those. Two elements are equivalent if, now we've introduced a new symbol, a wiggle. Let me call this now x wiggle y is what we will say means x is equivalent to y. That's the notation. And for x to be equivalent to y, we want three different properties. We want x to be equivalent to itself for all elements. If x is equivalent to y, then that implies that y is equivalent to x. We don't want any kind of slot dependency, meaning first slot equivalent to the second slot. We want that to mean that the second slot is also equivalent to the first slot if you sort of view left and right sides of that wiggle as slots, and that's true for all x and y. And the third property, if x is equivalent to y and y is equivalent to z, then that implies that x is equivalent to z. And that needs to be true for all x, y, and z. And in fact, one can create an infinite number of definitions this way. There are an infinite number of possible definitions of what makes two elements equivalent. Whatever that definition means, or the rule, we just need it to obey those three properties. The rule just has to obey property A, property B, and property C. Where now, if we apply this, or application of an equivalence rule, can actually create equivalence sets or equivalence classes. So that now if we had a set S sub x, we could build that or create that by saying, oh, this is the set of functions y such that y is equivalent to x. And these equivalence sets form a partition. Or we can go the other way. Any way that we partition a set forms these equivalents, forms an equivalence rule. So also, any partition defines an equivalence rule. Let's look at how we might do that. Suppose that we now have the following set, and the following set is in fact the set of integers. So consider the underlying set of integers, so that our set S is now n, where n can take on 0, plus or minus 1, plus or minus 2, etc. That's now our underlying set, and now we want to partition that or separate it up into parts or into equivalence sets. We could do a modulo 2 or a mod 2 congruence on that set of integers. A modulo 2 congruence generates 2 equivalence sets. Where now we have one set, let's call that S sub 1, is the set of n's such that we have plus and minus 1, plus and minus 3, plus and minus 5, etc. And those now, mod 2, would all just be 1. The other set of integers is now 0, plus and minus 2, plus and minus 4. So if we were doing mod 2 on any integer, if the remainder came back 0, then we would be in set 2. Or we could think of this now as just a fancy way of saying you've just partitioned the integers into a set of even integers and a set of odd integers. That's all we've really done with this rule of mod 2 congruence. What's another example of a way to partition a set of signals? Suppose this one, let's consider the following sort of trivial waveform that we're going to just throw out. Consider the set of all signals except for what we will refer to as, and this is in quotes, a zero signal. A zero signal is defined to be the following. Let's say that that's now S sub 0. That's the set of functions x that at time t sub 0 equal 0. Let's not even include those functions or those waveforms in our set of all signals. So consider the set of all signals except for signals in this zero signal set. So if you have a signal that has a value of 0 at t0, we're not even going to classify that. We're just neglecting that set. But in the collection of all the other signals, let's now define. We can now define. So this is, in terms of what this really amounts to, these are the signals that equal 0 at time t equal t sub 0. Let's not even worry about those. We can if we want to, but let's, for cleanness of discussion, let's just throw those out and not even consider those. But now we can define in the other signals that are left, which are all signals, except for this unique little piece, we can define a partition. In what way? Well, let's say that we now have an S sub positive. And now that's the set of X, set of waveforms, such that if you looked at that waveform at time instant t sub 0, it would have a value that's positive, bigger than 0. And let's now say that the other partition is now what we will call S sub minus. That's the set of waveforms or functions such that at time t sub 0, our particular function is negative at time instant t0. Doesn't matter what it's doing any other time, we're just partitioning the set of all signals such that we look at one time instant, t0, and at that time instant, if the signal is positive, we throw it into the S sub p. If the signal's negative, we throw it into the S sub minus. If it's 0, we just forget about it. But we could have a rule that says, oh, just group that with the S plus, or group that with S minus. But we're just neglecting that at this point. So that now this partition can be used to define an equivalence rule. X is equivalent to Y if, now here is our equivalence rule, if we take the waveform X at time instant t sub 0, and we take the function Y at time t sub 0, then those two waveforms will both belong to X plus, or they'll both belong to, S plus or S minus if this particular product is what? So if we want X and Y to be equivalent, what do we want this product to be? How could we create a rule out of this product? So as long as we have X and Y both positive, or X and Y both negative, two negatives make a positive, as long as their product is positive, both of those signals will be equivalent, meaning they're both going to be in either S plus or they're both going to be in S minus. If we get a negative result, they're in different bins, aren't they? Or in different sets. And that you can easily sort of just create an example of some signals that you want to now partition into S plus and S minus. Meaning maybe we just draw an axis and this is now time, and maybe we're interested between A and B, possibly. Let me say that we now have f1. Let's say that's one of our functions, f1. And then we have a function that's f2, and maybe that one looks like this. And maybe f3 looks like that. Maybe what I should have done before I start doing, well, I never know where to start this. Let's say that the next one is f4, and it's down here. And maybe our T naught, which we hadn't yet defined, let's define that. To be that instant of time. So this is now T naught. And it's, I hope, fairly straightforward to start assigning these functions, f1, f2, and f3, and f4, into the particular set that it belongs to. What's f1 belong to? f1 at time instant t0, f1 is bigger than 0, isn't it? So it's now going to be an element of s sub p, or s sub positive. f sub 2, a lot of its time it's negative, but what happens at instant t naught? It's positive, so f sub 2 is also s sub positive. f sub 3, f sub 3, I've got it, don't even have it showing as far as its label, but what's its value at t naught? So that one belongs to s sub minus, s sub 4. And now we can start talking about which of these signals, f1 through f4, are equivalent. f1 is equivalent to, we've just created two equivalence classes. It's either yes or no, and if they're both in S plus, then they're equivalent. So f1 is equivalent to f2 since, and now we could apply the rule, f1 at t naught times f sub 2 at t naught is in fact positive. What about f1 and f sub 3? Are they equivalent? No, they belong to two different sets, so let's say not wiggle, wiggle not. So you can't wiggle, if you're F1 and F3, they are not equivalent, since if you looked at the product of f of t naught with f sub 3 of t naught, that's negative. When you're building these equivalence classes, it's really not that critical what you pick to be sort of the base case. So note that equivalence sets or equivalence classes can be represented by a characteristic member. Where we might call that characteristic member x hat. And so now we could create a set based on x hat. Or we could now say that we want all signals x that are equivalent to x hat to be one of the sets in our partition of this underlying set. And it really does not matter what we picked for x hat or which x hat is used. Now we have signals. We have the ability to partition this set of signals into sets by equivalence relations or rules. Now let's talk about introducing a distance. How close are signals to each other? Or now we want to be talking about signal spaces. And now we've jumped into chapter 2. Or we now have sets of signals or signal sets and this notion or a notion of distance. And that's going to now give us signal space. Or let's now create this distance or metric. A distance definition, let's say d is what we will call the distance. D is referred to as a metric if we looked at two functions, x and y, and their distance is greater than or equal to 0, and if their distance in this metric is equal to 0, that's true only if and only if x is equal to y almost everywhere. So pointwise correlation, they may miss in a few places, but here we're going to assume that they're equal almost everywhere. They could differ in a finite number of places. B, the distance between x and y or this metric is going to be symmetric, meaning d of xy is equal to d of yx. So it's non-negative in part A, the distance between two functions in our set. It's symmetric. Whether we put it in the first slot or the second slot, it shouldn't matter. And we have a triangle inequality relative to this metric. D of xz is now going to be less than or equal to d of xy plus d of yz. And what are some of these distances? And you could think of these as functionals. You're now translating, taking a function or two functions and mapping those onto a scalar. And that's what we were calling a functional. So that we might have d sub 1 of two waveforms x and y, we could define that to be this integral from a to b of the absolute value of x of t minus y of t, let's say raised to the first power dt. And then we'll take the first root of that. I'm just emphasizing what we're going to do in subsequent indexed versions of d. This we could call the L1 metric. The L2 metric, or the Euclidean distance, d sub 2, is now wherever we, well, I can't say everywhere we saw a 1, replace it with a 2 because of that 1 over 1, but in the denominator of that 1 over 1, put a 2. We now have the integral from a to b of the absolute value of x minus, or x minus y absolute value, now square that, integrate that quantity, and then take the square root. That's now the L2 metric, or a Euclidean metric. And we could just keep going, a d3, d4, etc., and if we take it to the limit, we could have a d sub infinity of xy, and now we are looking at the supremum of the absolute value of the difference between x and y, where this supremum, I'm avoiding saying soup because it's too close to mealtime, but sometimes it's abbreviated as soup, but supremum is just really the least upper bound. And by that, I'm simply saying, suppose that you had a x of t minus y of t. Maybe that's what this is. This is now x of t minus y of t. And you could find its absolute value, which would flip all of those lower humps to be positive. I'm not going to worry about that. But somebody could say, oh, there's an upper bound to that, and that upper bound is right here. And maybe this is 7. But is that the least upper bound? No, we can reduce that so that now maybe it turns out that that's now the least of our upper bounds, and that one, let's say, is now 4. So this 4 is the least upper bound of this distance between x and y. So that's the soup, the least upper bound. And what we can play with now is if we now have a set of elements, again, these sets could be band limited, energy limited, sinusoidal, a set of elements plus a metric. Now we could say, oh, we have the set of continuous waveforms with a L1 metric plus a metric. Now we have a metric space. And we might say that that's now the set S with a particular metric D. And what you can find, or what you then can see is that if you have the same set, maybe we have sinusoids, but if in one case somebody uses an L1 metric and in another case somebody uses an L2 metric, we have different metric spaces, even though they're both working with the set of sinusoids. So you can have a same set but a different metric, and that's going to imply that you have different metric spaces. Meaning you could have a set S with a metric D1. You could have the same set S with a metric D2, or you could have a set S with the infinity metric. And these are all different metric spaces. And now if we had a complete metric space, we would have a Banach space. If we had a complete inner product metric space, put an inner product on this, which now might be this L2 and maybe nothing else in terms of the L's, then we would have a Hilbert space. That's now connecting what we've talked about in the finite dimensional with the infinite dimensional, and we'll have to stop at that point since we're out of time, but I think you now have the foundation to start moving forward with functional analysis or functional ideas based on infinite dimensional spaces.